Good morning. We are looking at energy, and we finished chapter 7. We're moving on to chapter 8, more energy that we're going to be talking about. This chapter specifically gets called conservation of energy, and we had started looking at some of this energy conservation stuff in the previous chapter, so this will be a much more detailed, much more thorough look. So now I think what this picture is supposed to represent here, right, we got this pole vaulter and they run, so they acquire a bunch of kinetic energy and then they're sticking that pole in. I guess we're getting some redirection of that kinetic energy up and over the bar. We'll take a look and see what this looks like. Here's a list of all these topics. I think we can move through those. Again, you can use those for your reference. But we're going to start off with taking a look at forces. Now, in chapter 7, we had been looking at work. And so we were looking at energy transfers that were taking place. And now we want to take a closer look at certain types of forces. So we want to classify forces as being either conservative or non-conservative. Not conservative and liberal, but conservative and non-conservative. So a conservative force is characterized by having the force acting on an object while it's being moved from one location to another, that it's independent of the path taken. Now, the example that they have right here is that they've got an object sitting on a table or something, and there's a certain height. And so, you know, here's a textbook, and it's sitting on the table. And so this represents a certain amount of potential energy. And then what happens is, if we lift the book up, that required a certain amount of work. Now, the energy transfer that we put into this book, lifting it up to this elevation, it didn't show up as kinetic energy, it showed up as potential energy. So there's energy here that the book didn't have when it was on at the lower elevation. Now, specifically, this sort of work it's pushing two objects away from each other. I know the emphasis here is on the book, but in some sense we're taking the book and the earth and we're separating them by some distance, and then we're allowing them to come back together, and we're saying that it required work to separate these two objects, and now we can get that work back by allowing them to come back together. And so a force is conservative if, you know, we take this object and we lift it to this height, and that required a certain amount of energy. Well, what if we did a different path? What if we, first of all, rolled this, you know, the object up some kind of a ramp, and then once we got to the top of the ramp, we moved it back over to this location? How much work would that take? And it turns out that for gravitational forces, it's the very same amount of work. Raising an object from a lower elevation to a higher elevation, the amount of work required is independent of what path we take. So we could lift it up a little bit of distance, and then we could move it around in some circles, and we could lift it a little farther. At the end of the day, if we keep track of all the work required to lift it, and then move it sideways, and then move it back up. And so the sideways motions don't require work, but anytime we move opposite the gravitational field, that is going to require work for us. So that means that gravitational forces fall into the category of a conservative force. Now, what's interesting about conservative forces is anytime we have a conservative force, we can define a potential energy. We can treat the force as if it's able to store energy when the objects gravitationally, if they're separated, we've stored energy. If we allow them to come back together, then that energy is taken out of that system. So that's kind of this first example and the idea of conservative and non-conservative forces. Here is another way of thinking about conservative forces. It says a force is conservative if the network required for moving an object around a closed path is zero. So what that says is, again, if this is gravitation, we could take an object at a lower elevation and we could lift this object up whatever shape path we want until we get to location 2. That's going to require a certain amount of work. And it doesn't matter which path we took. On the way back down, well, I guess this is 2 separate paths up. So we could take a different path up. What we'll find is that this path requires just the same amount of energy transfer as this one. Again, if it's gravitation, the sideways motions don't really require any work at all. It's only when we create displacements in the direction of the gravitational field. So if we move upwards through a gravitational field, no matter what path we take, getting to that other elevation is going to require a certain amount of work. When we allow an object to come back down, so okay, so I think these 2 arrows are both up, and so it's saying either path requires the same amount of energy. And then it's saying if we move this to a closed path, where we go up along path A and come back on path B, that's going to work out, that's going to zero out. Because the energy that we put into going up, we can get back on the way down. Now when objects are dropping through a gravitational field, a couple different things could happen. So that energy could become kinetic energy. So the object, as it gets pulled down through a gravitational field, that energy could go into the object and increase its kinetic energy. Another possibility is that we could just lift the object, or not really lift, but lower the object from the higher elevation down. In that case, we would be taking energy out of the system as it lowers back down. Okay, now what's an example of a non-conservative force? What kind of forces don't operate that way? Maybe all forces do. Well, they don't. And so friction, for example, friction is an example of a non-conservative force. If we start at location 1 and we identify some other point on the floor over here, the energy that's going to be required to get from position 1 to position 2 is going to depend on what path we take. So if we take a direct path, it's shorter, and the amount of energy we'll lose due to the frictional force probably will be less if we take a shorter path. If we move back and forth along the floor, along a different, longer path, that's probably going to require more work. You know, if the frictional forces are uniform everywhere on the floor, then no matter what path we take, the energy is not being stored by the frictional force. The energy actually is going into thermal energy. And so if I go from point 1 to point 2, energy is lost due to friction. Thermal energy is generated. If I go from point 2 back to point 1, I lose that energy all over again. I mean, not the same energy, but I lose additional energy. So friction is not a conservative force. It doesn't store energy in something. So that is a force that is always going to be losing energy, no matter which direction we operate in. If I drive an automobile up to the top of a hill, I have the gravitational force was conservative, and that means that I have stored energy, potential energy in the car. On the way back down, that gravitation will return the energy to my car. But that's not going to happen with friction. I'm going to lose energy due to friction on the way up. I'm going to lose energy due to friction on the way back down. Okay? So conservative forces, here's some examples here. Gravitational forces are conservative. Electric forces are conservative. Now I added in magnetic and nuclear forces. So it turns out all of the fundamental forces of nature are conservative, meaning that we can use those forces to store energy, and then we can recover the energy that's been stored in those forces. If I'm running a chemical reaction, then the energies that are, the forces that are holding the atoms and molecules together, those are electric and magnetic forces. And I can get the energy back. I can take a chemical reaction, I can reverse it. In one direction if it's releasing energy, then in the other direction it's going to require energy as an input. And so energy is conserved. So if we're dealing with gravitational forces, we can use energy conservation, electric forces, magnetic, and nuclear forces. Now, there's also this force called elastic force. Now they threw that in. Elastic force is not one of the fundamental forces of nature. But the elastic force is the force that we're going to use in those springs that we saw last chapter. So we're going to be looking at examples of storing energy in spring systems. Anything that has an elasticity to it, you could imagine storing some energy in that. And these elastic forces are electric and magnetic in nature. Anything where we're depending on forces acting between the atoms and molecules are going to be electric and magnetic in nature. Now, the non-conservative forces, we've got forces here that we're just going to lose energy to. So examples of these are things like friction, air resistance, well, I'm going to stick with these resistive forces up here, push or pull by a person. So these forces don't have a well-defined energy associated with a particular configuration of objects. The way that if I have a set of charges in motion, there's going to be a certain amount of energy stored. If there's a certain set of masses distributed gravitationally, there's going to be some gravitational energy that's stored within those. Same thing with nuclear forces. Okay, so where we're headed with this is that we're introducing the idea of a potential energy. Now, the kinetic energy, that made sense. Kinetic energy made sense because, hey, something's moving, and we could say that it's moving faster, or if it has more mass and it's moving, that represents more kinetic energy. But the potential energy idea is, here it says potential energy by virtue of its surroundings. I want to say potential energy in terms of how objects are arranged. Whether they're arranged so that they're closer to each other or farther away, that's going to determine how much gravitational potential energy the system has, how much electric, how much magnetic potential energy the system has. So here's a gravitational example. So here's an object, and then it's been lifted to this location, and then it's lifted to here. And what we're doing is we're keeping track of displacements. So there's a displacement that's taking place for this, and there's a force that's being exerted on the object as it's being lifted from the lower elevation towards the higher elevations. Now there's a gravitational force also acting on this object. So gravity is pulling the object downwards, and then there's a force that the person is exerting in the upwards direction. So one way to think about this is, if we take an object, a mass, with an object with mass m to a height h, the work that we would necessarily need to do would be equal to the force. That's just the force that the hand's exerting. So it's a force dotted with the distance, Now, in this example, the force and the distance are in the same direction. We'll write that as mg, that's the force that we would need to lift with, times the distance, times the cosine of the angle. Now, the angle in this case is 0 degrees, but what we just said was I don't have to lift this vertically. I could lift this along a different path. If I lift it along a different path, I'm going to have to carry out an integration of the force, integrated over that particular path. But because it's a conservative force, what we're guaranteed is that whichever path I use in taking the object from this elevation, y1, to this elevation, y2, separated by a distance h, that's going to give me the energy that we need to put in will be given by mgh, or mg y2 minus y1, where the y2 and the y1, those are the elevations that we're lifting the object between. So we therefore define this as a gravitational potential energy given by a height. Now here they've called it y. They've also used the symbol h, and we'll see both of these get used. So we'll see sometimes we'll be using y as a variable. We can just use x. We don't have to use y just because it's vertical. And then h gets used a lot too to represent how much gravitational potential energy we have. Now notice what's happening with this gravitational potential energy is it's a difference in energy between two locations. It's there's a certain amount of gravitational potential here and potential energy here, and then we're really thinking in terms of a difference. Now, the potential energy can be converted back into kinetic energy if the object is dropped. So that's what we had mentioned before, is if I lift this object up, I'm transferring energy in, the gravitational force is taking energy out and it's storing it. So that's going to get stored as gravitational potential energy. And then when it's at the higher elevation, I could lower it back down. Now if I lower it back down, then I'm taking out the energy as it goes back down. Or another possibility is we could just drop it. Which is what I mean, if we could lift this up, and then we could just let it fall back down. So we could lift the object up, the work that we did in lifting it, but then we could, well, I don't want to let it drop on this table, but we could let it drop onto the table, just slam down onto the table. That's taking a certain amount of potential energy and converting it into kinetic. Now, another question that they ask right here, they go, okay, if this is going to be the formula for potential energy, what's the coordinate system we're going to use? Where is y equal to 0? We have to decide what the y values will be, and it turns out that it doesn't really matter. As long as we're consistent about our coordinate system, we can pick y equals 0 anywhere we want. And that means that we can pick the y equals 0 location will be kind of by definition our reference in terms of potential energy. So we can actually define one level as being 0 potential energy. Anything higher would be positive values of potential energy, and anywhere lower could be negative. So we got to be ready to work in terms of positive or negative values of potential energy. That's what we're going to have. We're going to have positive or negative values as a possibility. Okay, so the reason we can do this is because differences or changes in potential energy from one height to the other, that's really the only thing that we need in order to do these problems. So I don't necessarily need to know specific values of y2 and y1 so much as I just really need to know the h in the MGH formula for potential energy. So here's an example with roller coasters. So let's head to the amusement park. Here is a roller coaster moving along. We're going to imagine that there's no friction, there's no non-conservative forces, no friction, no air resistance. So the only energies that we have to consider here are kinetic energies. So if this thing is moving, it's going to have a certain amount of kinetic energy. And then we can consider also potential energies. So we've got location 1, and then the roller coaster car makes its way up to the top at point 2, and then it drops a long ways down to elevation 3. Each of those elevations has a different amount of potential energy. So let's put some numbers in and see what happens here. It says that well, that's a 1,000-kilogram roller coaster. That's a pretty large amount of mass. So a 1,000-kilogram roller coaster moves from point 1 to point 2 to point 3. What's the gravitational potential energy at point 2 and 3 relative to point 1? What they mean by that is take y equals 0 at point 1. So we could start with, where the roller coaster is located right now as being our reference point. So that becomes a reference point. Now what that would say is by the time I get up to point 2, how would I calculate how much potential energy I have? And we could use that formula, we could use MGH. So I need to know the mass, I need to know the gravitational field, and I need to know the h value. Now at point 2, the h value would be 10 meters. We decided to call this the 0 height. So going up 10 meters from 0 would put us at a value of 10. So I can calculate that as MGH or MGY, where h or y is equal to 10 meters. What happens at point 3? If the 0 point is here, then anything above this would be considered positive gravitational potential energy. Anything lower would be negative gravitational potential energy. So let's see what the options are for this. So here I've drawn my diagram, and to begin with, I am going to call h1 the height associated with position 1, 2, 3. This is 0 meters. And then the height at the top then would be positive 10 meters above that. And h3 would be at negative 15 meters. That'd be 15 meters below the potential energy that we had defined. Now what I can do then is at each one of these points, I could define the gravitational potential energy as being mgh. And again, we could be using mgy as notation. That would say that at position 1, the gravitational potential energy, we're going to define that as 0 joules. Okay, so that is what my J's look like. They look like those. At position 2, it's not 0 anymore, so I'm going to put in the m, that's 1,000 kilograms, put in the gravitational field, 9.80 newtons per kilogram, and then put in the h or y value for that elevation. Now that's at an elevation of 10 meters above, and so that's going to be 98,000 joules of potential energy relative to 0 joules at position number 1. Okay. Now for position number 3, this is going to be the same 1,000 kilograms, 9.80 newtons per kilogram, minus 15 meters. That's going to give me a potential energy of minus 147,000 joules. So I'm not sure I answered their question right. Let me see. A says, what is the potential? Oh yeah, actually I did. So I did read the problem carefully. That happens. So these would be, if we've defined this as 0, what would be the potential energy at location 2? What would be the potential energy at location 3? Those are the numbers. Now in the part B, it said what would be the difference or the change in gravitational potential energy of point 3 relative to point 2. So if I take the potential energy here, minus 147,000 joules, and subtract off my starting potential energy, 98,000, I get a difference of 245,000. So there's that roller coaster drop right here. Here I am in the roller coaster and we drop. How much potential energy did we decrease during that rapid drop in the roller coaster? And we lost, we gave up 245,000 joules of potential energy. What happened to that? And ideally, all of that went into kinetic energy. So we picked up a lot of speed on the way down. Now, let's go back and look at positions 1 and 2. How did this thing get up to position 2? And there's a couple possibilities here. If it's a roller coaster, it could be that, they have that, that drive system that catches onto the roller coaster car and pulls it. So it could be that we had some mechanical system that grabbed the roller coaster car and lifted it up to this height. That's one possibility. How much energy would that have to have provided? That would have to have provided 98,000 joules of energy, because that's how much potential energy it's going to have at the top. So when we're designing the motor system, the mechanical system that's going to lift our roller coaster, we would have to make sure that it can provide that much energy over a reasonable amount of time. The riders on the roller coasters don't want to wait all day to get lifted up to this much higher elevation. All right. Another possibility is this could have been brought in at really high speed, right? We could have come in with lots of kinetic energy to start with, and then it's going so fast that the kinetic energy is able to lift the object up to this elevation. Now, how much kinetic energy are we talking about that the roller coaster car would need to come in with in order to reach the top? And again, we can come back to the energy numbers here. It says that if we're going to have the roller coaster come in with, and just as a result of its speed, it's going to be able to reach the top of the roller coaster at point 2, we're going to need 98,000 joules of kinetic energy. It's going to have to come in with at least 98,000 joules of kinetic energy if, by virtue of its speed, it is going to be able to reach that highest elevation. Okay, so you can kind of play around with the numbers here and imagine different scenarios as to how the energy is going to work out. What would happen if we decided to come back and redefine the 0 point? And you go, that's fine. You can do that in an energy problem. If we're analyzing this problem in terms of its energy, then at elevation 3, that's the lowest elevation, maybe we want to call that 0. If that's 0, then H1 would be 15, H2 would be 25. What would be the potential energies associated with those? How would we label the potential energies in that case? And in this case, it would be the potential energy at point 3, which is 0. And then by the time we have climbed 15 meters, this is telling us that a 15-meter climb would require plus 147,000 joules. So this would be 0. This would be 140,000, 47,000. And then what would this one be? And that would be the 245,000. Okay, so we can move these numbers around depending on where we've designated the 0 point for the height, and wherever we've done that is going to be the 0 point for the potential energy. Now, the general definition of gravitational potential energy looks something like this. It says that when an object is dropping, that energy, the work being done by gravity is going to, we're going to be taking energy out of the gravitational field in that case. So there's going to be work being done by gravity, and when work is being done by gravity, the potential energy is dropping. So it says that when something is dropping, the potential energy is decreasing. We can turn that around. If we instead lift the object up, then the work done by gravity is negative. But the minus sign here is telling us that the potential energy in that example will be increasing. So to calculate potential energy formulas, we can start by looking at the work being done by that conservative force. And if, in this case, it's the gravitational force that's being plugged in here. The one down here is more general. So this is the gravitational case. And now what we're going to do is say the same formula applies for any conservative force. So the gravitational force, we can calculate what that value is at different locations. If it's a different force, if it's an electric force or a magnetic force, a nuclear force, we can also plug in the formula for that particular force and use that to calculate what potential energy differences there will be. So the signs on the potential energy, the delta U's, and the work are going to be opposite in those cases. That's the thing to keep in mind here, is that there's a relative minus sign. And again, the minus signs here can be a little confusing, but just remind yourself that the minus sign is telling me if I allow the object to move in the direction of the force, my potential energy will be decreasing. So that's probably a good way to think about this too. If I think of this in terms of the dot product, so if F and dl are in the same direction, this inside the integral would be a positive quantity, and the potential energy will drop by that amount. Now the negative sign here means that the potential energy will be dropping. Okay, let's look at some more examples with that. Now there's a different potential energy associated with the spring. So we had looked at some springs, and we said, okay, here is the spring. Now they put a coordinate system right here. The one we're interested in here is the x-axis. This is going to be x equals 0. So we're going to designate the natural length of the spring as being x equals 0, having this end at that location. If we now compress the spring, then there's going to be a certain x value here. When we let the ball, when we put a ball next to the spring, I guess we compressed it with the ball in place, and then we let go. So what's happening in terms of energy in those diagrams? Well, here we didn't have any energy stored in the spring at all. And then we did a bunch of work and compressed the spring. So now I've got a compressed spring, and now I've got that energy stored. So the spring is able to store energy, and it stores energy in the electric and magnetic fields of its atoms and molecules. When we compress a spring, the atoms and molecule configuration, they're shifted a little bit, and what the spring would like to do is expand back out. The forces built into it are tending to push the spring back out to its natural length, but we're holding the spring, all the atoms and molecules that make up the spring, we're holding them all in place. Now when we let go, the spring is able to exert a force on this projectile, and the projectile gets shot back out. Let's see, a spring then has potential energy. They're going to call it elastic potential energy when it's compressed. Just call it the energy in the spring, whether it's compressed or whether it's stretched. Now the force required to stretch a spring is kx, and again we talked about the minus and plus signs here. You kind of have to gauge that on your own as you move through these examples. K is called the spring constant. I know at times I'm going to call it the force constant, so be prepared for that. And it needs to be measured for each spring, so each spring could be a different value of K. There's no constant value that applies to all springs. Individually, springs have their own individual spring constants. Now, the energy that we've stored here, let's try this same example. There's going to be a difference in potential energy between when the spring is compressed compared with when the spring is not compressed. To calculate that, we're going to take the force. Now, this is the spring itself. There's kind of two approaches here. The spring itself requires the minus sign here because the potential energy will increase when the force and displacement are opposite, and the potential energy will decrease if the force and displacement are in the same direction. If the spring is pushing something away, the force and the compressed spring is pushing something away, the force and the displacement are in the same direction, that would make this positive, and this is saying that the spring is losing its potential energy as it pushes an object away. And so this is minus kx dx. Now they've integrated that to get the 1/2 kx squared. With the minus sign out front here, that turns into 1/2 kx squared. And so if we're compressing the spring, then the F of the spring and the displacement are in opposite directions. That gives us a minus sign here and a minus sign here, and that gives us an increase in the potential energy. And so we can write that as 1/2 kx squared. Okay. So they do, this is written for the energy while we're compressing it. So here we're going from 0 to x. There's a minus sign here, cancels the minus sign here. So this is storing energy 1/2 kx squared. If we want to release the potential energy, then we can reverse the directions here. Then the force and the displacement are going to be in the same direction. That'll reverse the sign. It will be giving up an energy of 1/2 kx squared. So in any case, this is the formula that we can use for the spring potential energy, and that's going to be, if it's ideal, it's going to be given by 1/2 kx squared. All right, potential energies in one dimension then. The potential energy as a function of x can be written as minus whatever force it is that is storing the potential energy. So f of x integrated over the displacement, and then, you know, back in your calculus classes, you're used to having these constants of integration. So you realize that at the end of carrying out integration, you can always add an extra number into that. Well, in this formula, the constant of integration applies to whatever we've determined to be the 0 point in terms of potential energies. So this is kind of like saying that the constant of integration is arbitrary. We can decide what location to call 0 potential energy. Now this equation, we can flip this around, we can invert this equation so that we can show that the force then, if we differentiate both sides, the force then is given by minus du dx. So we can take a derivative of the potential energy expression. So the potential energy is going to depend on a location. For gravity, we saw that as a height. For the spring, we saw that as an amount that the spring is compressed. So the force, as a function of x then, can be calculated by looking at how the potential energy is varying as a function of position, specifically taking the derivative, and then putting a minus sign out front. So both these forces, these formulas, have minus signs on them. And again, that corresponds to if I allow, if I follow the direction of the force, let's say gravity. If I follow the direction of the gravitational force, which is what this is indicating, then my potential energy is going to be dropping. If I go opposite the direction of the force, then the potential energy will be increasing, is the way that will work. Now, in 3 dimensions, what this looks like then is, if I have a region of potential energy, I can take partial derivatives in the x direction, partial derivatives in the y direction, partial derivatives in the z direction, and then assign unit vectors to those. And the partial derivatives will give me the force components fx, fy, and fz. So here what we're using is the unit vectors I, j, k to keep track of those directions. Okay, so it all kind of fits together. It all kind of hangs together, going back and forth between the integrations. Going back and forth between the integrations and the differentiation. Now this is kind of the mathematics behind it, and you can come back and refer to these equations as needed. I think we're going to find that we can do a lot kind of independent of that. Whenever we have to come back and think carefully about how potential energies have been defined, we'll come back and look at those equations. Now, in mechanical systems, what we do is we look to see, are the forces conservative or are the forces non-conservative? Do we have a mix of both types of forces taking place? If none of the forces are non-conservative, then what we can do is say that the sum of the kinetic energies and the potential energies is a constant. So that if I look at the total amount of energy in a system, it's going to be a constant value throughout. The kinetic energy drops and the potential energy increases are correlated, and vice versa. So any change in the kinetic energy will be associated with a change in the potential energy, equal in magnitude, opposite in direction. So we say that a lot. So that allows us to define what we call the total mechanical energy of a system. So the total mechanical energy of a system includes adding together all of the kinetic energies and adding together all of the potential energies. And then if the energy is conserved, so let's think in terms of, what would this apply to? If this is the roller coaster, right? So what we found for the roller coaster is if there are no non-conservative forces, so let's see, what would be a non-conservative force that would have an effect on a roller coaster? Friction, air resistance. So if things like friction and air resistance are small effects, if those are things that are fairly negligible, then what we could do is say when we first launch that roller coaster, it's going to have a certain amount of kinetic energy, a certain amount of potential energy, let's say at location 1 along the way. Well, if it starts out with a certain amount of energy and none of the mechanical energy is leaving the system, then it must be conserved. So that would say that at point 2 along the roller coaster, if we add the kinetic energies and the potential energies, it equals the total amount that we started with. Now, if we do think back up to the roller coaster, so stare at that formula a bit. It's saying at each location along the way, if there are no non-conservative forces, no forces that have been removing energy from the mechanical system we're looking at, then if we start out with a certain amount of kinetic and potential energy here, what happens to kinetic and potential energy here? Well, the potential energy's gone up, and that means the kinetic energy will have dropped. So at point 2, we'll have more potential energy, but not so much kinetic energy. And then what happens at point 3? Wow, at point 3, the potential energy drops dramatically. And so if we're giving up a bunch of potential energy, we must be acquiring a lot of kinetic energy. So we can go through this from position 1 to position 2 to position 3. And we can keep track of how much kinetic energy we have and potential energy at different locations. So that's kind of the mathematics behind it. So again, the principle of conservation of mechanical energy, if only conservative forces are involved, they're the ones that are exerting forces on objects and transferring energy, then the total mechanical energy of a system will remain constant, and that's what we call energy conservation for that particular system. So here's an example, and it's not a roller coaster anymore, now it's a really big rock. In the image, that looks really heavy. How is that person holding that? I have no idea. It probably weighs more than our textbook. So here is a big rock, big stone that the person has lifted, and look, they even got a little bit of a boost. They stood on a stool, which gives them a little bit of a boost. So here they are at one elevation, and we're going to call that H. And then here is a lower elevation, and we're going to call that one 0, and H is the distance between those two. What happens is when we first start out, notice this starts out with no kinetic energy. It's not moving, so there's no kinetic energy there, but it has a bunch of potential energy. Now, halfway down, we know that the potential energy will only be half as much. Potential energy over short distances in Earth's gravitational field is given by mgy, let's say, so we'll use y as a variable here. And that says that by the time I've dropped halfway, well, half the potential energy is gone. And by the time I've dropped all the way to the floor, I've used up all of the potential energy. So I'm going from starting total potential energy, half of it's gone, all of it's gone. Now, we could have, the potential energy just drops gradually as you move along the y-axis. It's just going to steadily drop off until you hit that 0 point. Well, what does that say about the kinetic energy? So if energy conservation works, which it does, then the kinetic energy here started out at 0. Whatever potential energy is missing, it must have gone over and gotten converted to kinetic energy. So halfway down, half the energy is potential, half the energy is kinetic. That provides us a way to find out what speed the object will be traveling. How fast is it going to be traveling? Well, we'll find out how much kinetic energy it has, and then we'll take that kinetic energy and solve for v. So that seems pretty handy. Now, it's based on the laws of motion, these definitions of kinetic and potential energy, and that means that we could do this by using forces and acceleration. So, the example that we have right here, we could go back and just work in terms of accelerations and velocities. That would also work. But there are going to be more examples coming up where it's harder. It gets harder and harder sometimes to keep track of all the forces and the accelerations. Practice when you can, doing both methods. But there are going to be some methods where energy conservation is probably the only straightforward, kind of easy way to keep track of all of this. All right, so here is that energy, kinetic plus potential. 1/2 mv squared plus mgy at each location. And I guess we never got to the bottom here. When we get to the bottom, all the potential energy is gone. It's all been converted to kinetic energy. So at any elevation, it's going to be pretty straightforward for us to write down how much potential energy we're talking about or how much kinetic energy we're talking about for a particular example. All right, so here is that falling rock again, and what we're saying is the original height is 3 meters. So the person stood up on that stool and they got the rock all the way up to, how did they, 3 meters is like 9 or 10 feet. Does that look 9 or 10 feet high? Maybe if that person's 8 feet tall. Anyway, somehow, this is at 3 meters. They needed a taller stool if they're going to say 3 meters. So this is going to start off at 3 meters and calculate the rock's speed when it has fallen to a point 1 meter above the ground. And so, let's see. If this is 3 meters, this is 2 meters, this is 1 meter, this is 0. Maybe we should just calculate a series of velocities and see how this problem is going to work. So let's do that. What we'll do is we'll start at point A. That was at a height of 3 meters. And then point B, this is the one they're interested in. It says it's at a height of 1 meter. I want to also say, point C. So that's going to be a height of 0. So let's see what we could say here. Let's say the total mechanical energy at A equals the total mechanical energy at B, total mechanical energy at C. At each of those locations, the total mechanical energy is a combination of kinetic and potential, kinetic and potential, kinetic and potential. Now, the only potential energy we have is gravitational, and then the kinetic energies are all going to be 1/2 mv squared. So let's try this. At point A, we're going to start off with the rock at rest, and that says it has no kinetic energy. But at point A, we have potential energy given by mgh. If this object is, they said 5 kilograms, so it's a 5, so it's not, that's got to be more than 5 kilograms, unless the thing's hollow. All right, I'm skeptical about the 3 meters, not sure about the mass being 5 kilograms. Where did they say, did I add 5 kilograms in? Maybe I did. Okay, I'm skeptical about that number, and it looks like maybe I added it. So it says 5 kilograms, it looks more like 50. I don't know where I got 5 from. But the potential energy at point A is 147 joules. That's what we have to work with. Now, by the time we get to point B, then we can reevaluate these energies. At point B, the potential energy now is going to be, the 5 kilograms, 9.8 newtons per kilogram. We're only at an elevation of 1 meter, and that means that the potential energy, the 147 joules that we used to have, only 49 of those are still potential energy. So that says that the kinetic energy then would come from taking that difference. We no longer have the 147, we can subtract off the 49, and that leaves us with 98. So what we've done here is I've taken the energies we started with and set them equal to the energies at a lower elevation. And just as a quick review here, Ka was 0, so that canceled out. That is gone. And so I'm trying to calculate Kb. Kb is going to be UA, potential energy that we started with, minus UB. And, it's right here. And so Kb is UA minus UB, and we calculated the UA, we calculated the UB. That's how much kinetic energy we're going to have. It's 98 joules. Plugging that into the velocity formula says 2 times the kinetic energy over the mass, square root, it's going to be going 4.43 meters per second. Okay, so that's using energy techniques to calculate how fast this thing will be traveling. Now, I think we mentioned this back in chapter 7, is that sometimes it's difficult for students to move on and from chapters 4 and 5 and 6 and start practicing these new techniques in chapters 7 and 8. And I was one of those students. When I first took physics in college, so it was my freshman year in college, and physics was fun. You know, I had not taken it in high school. I was a chemistry major at the time. I had not taken physics, and I kind of stayed away from physics almost because people said, well, that's for, you know, that's for people who are going into construction or they're going into building things. And I thought, well, building things is pretty interesting, but I'm really interested in the chemistry stuff. So I didn't get very involved in physics at the time. People, you know, I was told that physics was like building bridges and building buildings, and I thought, well, that's really cool. But eventually I knew I would be taking some physics. But in any case, I got to college, took my first physics class, and I just thought, wow, this is really fun. And I really enjoyed the kinematics, and I really enjoyed the forces. And then I hit energy. And energy was a little confusing for me. So looking back, I realized what I needed to do was practice more. I needed to practice these new energy techniques just to give myself some time to get familiar with how it worked. But instead, kind of what I was trying to do was solve problems using forces. So I didn't practice the energy problems as best I could. Things didn't go well on that midterm, but then I recovered from it. And in any case, I'm encouraging you guys to, when you see these problems like this, and you go, well, what you should be doing is both approaches. So practice using these new energy formulas. So practice all of these new techniques, and then go back and say, how would I have solved this back in chapter 3? Or chapter 4 or 5, more likely. So go back to chapter 4 or 5 and practice solving it there. And you'll see that the formulas all match up. And that's because they're all coming from the same source. All the formulas that we've used here to define energy are the formulas from, you know, Newton's formulas from motion and from gravitational forces. So anyway, practice both methods. Make sure you're getting in and really working at these new energy techniques. Here's another example we can look at. Here's a roller coaster, and we want to determine how fast is it traveling, and we want to use these new energy conservation techniques. So what we'll say is that we've got a hill, and the hill is, oh my gosh, this is 40 meters high. That's a pretty good sized roller coaster. And the roller coaster starts from rest. So, you know, there was some mechanical system pulling the roller coaster up to here, and then it's pretty much at rest. It's just barely moving, and then it goes over the edge. And then it is going to drop. Now, notice, with this roller coaster, we don't need to know any details about how steep. Maybe it's kind of steep, maybe it's really steep. All we need to know is how much of a drop do we have. Now that's interesting, because if I were to solve this problem, say back in chapter 4, this would be a really, really difficult problem. Well, let's do a quick comparison here. See this problem back here? That one I could solve back in chapter 4, because what's happening here is the force is constant, right? And that means the acceleration would be constant. And that means I could use formulas for constant acceleration. So I do a force diagram, I would determine the accelerations, and from that I could calculate what the velocities are. But this would be really hard, because the force diagram would be shifted a little bit at each location. So I would need to know something about the slope of the roller coaster at every location. I would need to know exactly what the shape of the roller coaster is in order to add together all those accelerations. What energy conservation tells us is, since gravity is a conservative force, it doesn't matter the details of how steep this is or how tightly curved. Now, it does make a difference that the roller coaster needs to drop in a way where the non-conservative forces are negligible. So I need to make sure that the friction is zero, basically, that it can be ignored. I need to make sure the air resistance can be ignored. If we drop this gradually versus dropping it very steeply, dropping it gradually will result in the frictional forces playing a bigger role. So, but if I make the assumption that the frictional forces are going to be small, everything's really well lubricated, and the air resistance is going to be small, it turns out the details of this don't matter. All I need to know is the height. So this is one of those examples where energy conservation steps up and says, you know, you're not going to be able to solve this using force and acceleration. You got to use energy conservation for something like this. So we want to find out what's the speed of the roller coaster at the bottom of the hill, and at what height would it be at when it has half this speed. Now they've told us in the problem, they're suggesting to set y equals 0 at the bottom of the hill. So I guess y equals 0 is right there. We don't have to do that, but we probably will. That seems like a sensible way to set up the problem, so it's probably not so difficult to solve. So let's do this. I'm going to get this diagram set up. Now, if I'm doing my energy conservation examples, which I am here, so with the roller coaster, I'm going to designate locations. I'm going to call this point A, maybe I'll call this point B, maybe that's it. That's all we need in this problem. At point A, what are the relevant numbers here? Well, point A starts at a height of 40 meters, and the object starts with a velocity of 0. That's the given information. What I can do using energy conservation is saying if I add together the kinetic and potential energies at A, all the mechanical energy, and then if I add together the potential and kinetic energies at B, all of the potential energy, they're going to be the same thing. Now, maybe what you're wondering, and I think you should be wondering, is, well, sure, this is kind of ideal, but in the real world then, does energy conservation just become useless? And it doesn't. So what happens is, if I have non-conservative forces, let's say that there is friction, there is air resistance, how can I make energy conservation still work? And what I can do is say, here's all the energy I start with. Here is the mechanical energy I start with, but along the way, some of that energy became friction, and some of the energy was lost due to the air resistance. If there are non-conservative terms, what we can do is we can estimate those and add those to the energy conservation formula. So the bottom line is conservation energy overall is always conserved. In some examples, like the one we have here, that's a relatively easy way to use energy conservation, and that's because we're ignoring friction, we're ignoring non-conservative forces. Okay, so this is a relatively easy example, and as we get to see more examples, we'll start to put those frictional forces back in and see how they work. Okay, so we actually use that, I think, back in chapter 7 in one of the examples. We'll get back to including friction again. But for right now, kinetic plus potential at A equals kinetic plus potential at B. Now often, one or more of these terms will just drop out. So let's take a look. We started at rest. Well, if I'm starting at rest, I don't have any kinetic energy. That term dropped out. So Ka is gone. So I can just cross that out. Similarly, we define the low point here as h equals 0 meters. So if this is h equals 0, then at the lower elevation, potential energy drops out. So I started with 4 energy terms: kinetic potential, kinetic potential. The kinetic energy that I started with was 0. The potential that we end up with is 0. So this is kind of a simpler version of one of these energy conservation problems. It says that the potential energy that we start with at the top, at the bottom, will be completely converted into kinetic energy. So I can write down mgh to designate how much energy we had, potential energy, at the top, and then at the bottom, we'll call that kinetic energy 1/2 mv squared. So with this formula, the m's cancel out. I'm solving for velocity, so I'm going to bring that over. I'm going to switch sides and bring the velocity over here. The 2gh goes to the right side. The masses did cancel out, and so the velocity then is given by 2gh square root. I can put those numbers in. There's my factor of 2. There's Earth's gravitational field. There is the 40-meter drop. The velocity we're predicting here is 28 meters per second, 28.0 meters per second at the bottom. Now, you may remember this looks a lot like formulas from chapter 3, or actually chapter 2, when we first started dropping things in gravitational fields. And you'd be right, because it turns out that this is the gravitational mass of the object. This is the inertial mass, and they cancel out. And we've talked about that before, that in a gravitational field, everything accelerates at the same rate. If we ignore other forces, gravitational fields left to themselves accelerate everything at the same rate. And we had mentioned that Earth is a reasonable place to practice this, but the moon is better because the moon has no atmosphere. And so when you drop things on the moon, they just drop side by side. You drop a feather, you drop a steel sphere that's this big, and a feather right next to it, they just drop right together at the same rate. And so energy conservation is leading us to the formula that says, hey, this roller coaster that went down this incline and then ended up at the bottom here at 28.0 meters per second, how fast would that have been traveling if instead of sending it down the roller coaster, what if we lifted it off and just dropped it? So if we lift the roller coaster off and drop it 40 meters, it's going to have the same speed. So what was it that the roller coaster track did? It just redirected the roller coaster. If there are no non-conservative forces, if friction and air resistance are negligible, it doesn't matter what path it follows from this elevation to this one. It could follow a curvy path. It could just drop straight down. But by the time it gets there, it'll be traveling at 28 meters per second. Now, this path takes longer because it's not picking up speed at the same rate. This path would be quicker to the bottom, but at the elevation of 0, either way, it's going to be traveling at 28 meters per second. All right, now in the problem, they also ask us this. They ask us about speeds at different heights. So I took this formula and I said, what if we have dropped, I guess you got to flip this around a bit. So we could take this formula and say h is the distance we have dropped. And so I did that. Because we're assuming that we're going to end up at 0 potential energy. So if h1 is the distance that we dropped and h2 is a different distance that we dropped, how would the velocities compare? And if we were to drop 40 meters, let's compare that with dropping just 20 meters. So that would be halfway down. That would be a factor of 2. Now, if we drop halfway down, what would the velocity be? And what this formula, this ratio formula is telling us, is that dropping twice as far increases the speed not by a factor of 2. Dropping twice as far increases the speed by a square root of 2. And so putting those numbers in, I went in and solved for V1, it says that halfway down, we would have been traveling at 70% of the final value. It would have been at 19.8 meters per second. Okay. Let me take a quick look at the clock here and see. I think we are probably at a place, we'll probably end there for the day. See where we are. Oh yeah, we're definitely ready to wrap things up. So let's stop there. And in fact, next time we'll pick up, I'll probably do a quick review of this, and then we'll move farther into Chapter 8. If you guys have any questions, stop by office hours. We will get those looked at.